Hi, everyone, and thank you so much for joining us for our second webinar in our series, AI Applications in Earth System and Climate Science. Today's session will highlight research on precipitation. The idea for this series is to feature new applications of AI and machine learning tools in research from NOAA scientists and NOAA-supported investigators. So this series will be a way to share ideas, share new work, and connect with others in the field. We hope to showcase innovation by sharing cutting-edge applications of AI and machine learning that help us understand and address complex challenges. We're also aiming to work toward answering some overarching questions, like how is AI being leveraged as a tool in this research, and how are important partnerships across NOAA, the academic community, and private industry driving advancements in the AI and Earth and climate science space. And we really do want to emphasize our collaborations. NOAA scientists and programs have really strong partnerships across disciplines, across agencies, and with other institutions, and we're excited to showcase that. To start us off, I'd like to introduce the speakers for our first presentation. So I am going to stop sharing my screen and allow Andrew Rosenau to begin sharing his screen. So this is Andrew Rosenau. He's a research scientist at the Cooperative Institute for Severe and High Impact Weather Research and Operations with the University of Oklahoma, working with NOAA's National Severe Storms Laboratory. He will be presenting along with co-PI Peter Veals, a research assistant professor in the Department of Atmospheric Sciences at the University of Utah. So among other work in their portfolios, Andrew and Peter are working towards a project called Improving and Expanding Gridded Snowfall Analyses and Seasonal to Subseasonal Snowfall Forecasts, which is supported by the Climate Program Office's Climate Observations and Monitoring, or COM program. Their presentation today will highlight their work on winter precipitation, and we're excited to hear it. Thank you so much for being here to Andrew and Peter, and go ahead and take it away.
All right, thank you, Clara. I and my collaborator Peter Veals from the University of Utah today are going to talk about what's been a kind of a longer term effort here at NSSL that we have been reaching out for collaboration with to quantify winter precipitation. And in particular, I'm going to talk about how AI can support safer travel winter weather products. The work I'm going to present today is not just the two of us. I'd like to highlight the large number of people over the years that have been involved in stuff I'm going to show you today. Unfortunately, don't have time to talk about their contributions individually, but this work would not be possible without everybody on this slide. To motivate this, I'd like to talk a bit about the human cost of winter travel. The figure here on the right is the annual number of fatalities over a 15-year period across the continental US. These are direct fatalities from lightning, tornadoes, floods, etc. And one of the things that's interesting about how we quantify fatalities due to weather is that we only really consider direct fatalities where the weather directly kills somebody. And somebody that dies in a traffic accident in the snow or in freezing rain, that's considered an indirect death. And so those aren't typically shown in figures like this or in statistics about winter or weather fatalities. If we are to include that, here's what that would look like on this scale. Over this time period, you averaged 817, or you had 817 fatalities, dwarfing the 600 for all the other causes over that time period combined. And this isn't just a problem for what we consider to be the snow belts or the areas that get a ton of snow. This is a gridded plot of where fatal winter weather crashes happened over a period of several decades. And you can see that it's not just areas where snow occurs, and it also depends on geography, the location of cities, the location of interstates, etc. And so in order to tackle this, we've been looking into what weather questions are important to winter weather safety. When we talk with stakeholders in winter travel safety, they generally are seeking answers to the following three questions. What will fall? Is it rain, ice, or snow? will it melt when it hits the ground, and how much is falling on the ground, whether it's ice, snow, or rain. And these questions are critical to establishing climatologies of impactful weather. So if we want to figure out where dangerous conditions happen, we have to be able to identify those dangerous conditions first before we can figure out how often those conditions are met. And this talk is going to touch on efforts underway to address each of these questions. In particular, I'm going to talk about how AI as a tool is filling in knowledge and observation gaps in winter weather. So the first question is, what is falling before it hits the ground? What hits the ground is actually a fairly difficult question. A number of you have probably seen this diagram before. It gets shared every single winter, and it explains how you get the four general precip types for winter: snow, sleet, freezing rain, and rain. And it's just a matter, at its most simplest, of where the below freezing and above freezing air is above the ground. But that's a problem, that it's so sensitive to temperature above the ground, because this is something that's rarely measured. It's usually weather balloons or aircraft that tell us what the temperature is above the ground. And even if we had perfect information on temperature above the ground, the precipitation type itself is difficult to observe. Our typical weather stations can only report rain, snow, or freezing rain with some error bars. Ice pellets or sleet require a human observer to make that report. And what is falling can change rapidly in space and time. You'll see things go from sleet to freezing rain, back to sleet to snow over a short distance or short period of time at the same location. AI has been used to create precipitation type algorithms. I've indicated a few that exist here, but something to keep in mind is that these are subject to the same observation issues. If we don't observe it, we can't build an AI trained on the data of those observations that don't exist. And in particular, there are almost no robust precipitation type observations above the ground. And this limits the aviation utility of an AI built technique for now. So for this piece of our puzzle, we're actually kind of sitting back and not jumping straight into AI. We're using something called the spectral bin classifier, which tracks particles as they fall from cloud top to the ground. And this allows us to keep track of changes that are produced as the particle falls. So it identifies on this sounding where we have temperature, dew point, and I've thrown on the freezing line. This yellow line's cloud top. And then the SBC starts at cloud top, drops the particles, and figures out whether it's liquid or frozen the whole way down. We could not do these pieces above ground very easily, if at all, from an AI perspective, just because we don't have the data. Now, what this allows us to do is create an analysis of precipitation type. I have an example here on the right from the SBC, and it can diagnose your classic precipitation types: rain, snow, ice pellets, and freezing rain, like I showed you on that diagram a few slides ago. But because we handle things by particle size, we track the small particles and large particles separately. This also enables us to track mixes: rain snow mix, ice pellet freezing rain mix, as well as drizzles. Freezing drizzles especially are important for aviation. These are also not very well observed by our current observation network. Speaking of that network, all of the dots on the figure to the right are surface observation stations. So if you're looking at observations in the here and now, those dots are the only places that you'll get precipitation type information. And if you look in the background, what you see, the coloration of the different precipitation types: green rain, blue snow, yellow ice pellet sleet, red freezing rain, and the rest are various drizzles or mixes. It's messy. And that is what winter weather often looks like when you get into transition zones between rain and snow. It varies a lot in space and time. And in fact, this mess created another mess. On this day, there was a 133 car pileup with 6 fatalities and 12 severe injuries in the DFW area, associated with freezing drizzle or light freezing rain. And so knowing the distinction between both the particle size and the precipitation type is critical for supporting travel safety. Second question is, will precipitation freeze or remain frozen? This is what our partners often tell us that, okay, great, you can tell us what's falling, but how is that going to impact the roads? And being able to tell them what's falling is more critical when the roadway supports ice. Knowing where the roadway is not going to melt ice allows the forecasters to focus their efforts on more impactful areas. So road temperature is measured by something called the Road Weather Information System, or RWIS. This is a picture of one on the right, a diagram on the left. And these are basically weather towers that measure wind and temperature and other meteorological variables, paired with a sensor in the pavement connected to that tower. And so you get the pavement temperature from this RWIS station. This has allowed us to develop what we call the probability of subfreezing roads, or ProbSR product. This is a machine learning product that utilizes a random forest algorithm that's trained on these RWIS data. It takes in a bunch of fields from the HER weather model as predictors to determine the probability that the road surface temperature is below freezing. And be very precise there, because does not predict the probability that road accumulates ice. It is just a piece of the puzzle if you want to actually figure out your travel conditions, but it is a very important piece of that puzzle. A random forest, for anyone that is not aware, is a machine learning technique where a series of decision trees are constructed based on training data. So if you, for instance, have a basket of fruit and you construct a random forest model to classify what fruit you're looking at, you'll look at things like size and shape and smell and color, and all of that gets put by a random forest model into a series of trees. And then when you go to classify some fruit that you're unsure of, you feed all that information through this random forest. It comes down through the trees, makes a bunch of decisions based on the parameters, and tells you the most likely classification for what you tried to run through the model. This is an example using a classification. ProbSR returns a number, which is a probability, but it's the same principle. You have a bunch of inputs, you create a decision tree, and at the end of those various trees, you end up with a number which represents the probability that that road surface is subfreezing. What model inputs does ProbSR use? I'm not going to dwell on this, but just know that it's a lot of inputs. It's not just things like temperature, it's wind speed and cloud cover and things like that. A lot goes into whether that road surface temperature. So I'm going to show an example here of what ProbSR looks like. This is a snow event across the Northeast. This is near the coast. You had a little bit of rain, but most of these radar echoes here were snow. And this is, for this case study, this is what ProbSR put out. And the brighter colors of the color in the background represent higher probabilities, or areas where the algorithm indicated it was more likely that the road surfaces were above freezing. Overlaid on this are RWIS observations. Black circles are below freezing observations. White circles are above freezing observations. And with the original version that we developed, we noticed that values were sometimes too low, and we investigated this and found that the problem was most pronounced in snow. So we identified a problem, have a solution, but how do you address this with inputs to AI? We have a probabilistic parameter we're developing, but this can be a challenge when the first thing is like, is it snow or is it rain? Those are categorical declarations. We want numbers. It turns out, as you dig into the HER model output, it actually produces the perfect quantity for this, the percentage of frozen precipitation. So a number between 0 and 100 as the percentage of precipitation that's falling, that is ice. And this numerical field fits the percentage goal of the algorithm. You're not trying to do the square peg into a round hole. You found the proper field to give you the answer you want. And so when you do this, retrain the algorithm, you go from the left, which is the old version of ProbSR, to a current version on the right. And you see a substantial increase in probabilities across the regions where the black circles are. Higher ProbSR values are now present where roads were sub-freezing. And so I want to emphasize that this is an example of how AI algorithms are improved like traditional ones. You find your shortcomings, you find data to represent that phenomenon and retrain the AI, and this might be a cycle that you have to go through multiple times to get the best answer. But we have a product that, when you look at the verification, which I don't have time to get into today, works very well. And then the final question is, okay, so we know it's falling. We know the environment it's falling into in terms of whether the roads are conducive to ice. How quickly is ice accumulating? How much liquid or solids are falling that will become ice? I'm going to break this up into two pieces. First of those being the freezing rain accumulation rate. As freezing rain hits the ground, how much of it freezes into ice? This has been an important area of research for us because as of right now, there's no current freezing rain analysis of record within the Weather Service. It's hard as an event is going on to figure out how much freezing rain has fallen at a given point if you don't have a report from that location. So we've developed what we call the Freezing Rain Accumulation National Analysis, or FRANA. This is an experimental national analysis, and this uses the multi-radar, multi-sensor, or MRMS, liquid precipitation, or quantitative precipitation estimate, QPE. So this is a system that has a lot of precipitation related products that's operational within the Weather Service, MRMSs, and this allows us to get that liquid precipitation value. We use the spectral bin classifier for precipitation type. And so an accumulation is just QPE times an ice to liquid ratio. I'll get back to what ILR is in a second. We validated this against ASOS surface station ice accumulations. So as I mentioned earlier, our surface stations, at least if they're so equipped, can report freezing rain. So we do have some observations, not everywhere, but some observations to validate this against. This is still experimental, but we are planning on transitioning this to operations soon. And we want to develop an AI-based ice to liquid ratio algorithm to improve on the existing method that is used in FRANA. So ice to liquid ratio, or ILR, this is the ratio of ice thickness to the depth of liquid that falls. Not all freezing rain, the liquid that falls, will freeze on contact. Some of it will run off. And this depends on a number of factors, including the temperature, the wind speed, the liquid precipitation rate, and more. On top of that, when you're thinking about ice accumulation, there's another issue that comes up, and that is it accumulates differently on different surfaces. On the top of the figure on the right is what we call radial ice thickness. When you have ice accumulating on a power line or a tree branch, it accumulates around that branch, and you measure that differently than when it falls onto a table or a roadway or a flat surface, what we call flat ice, which is the example on the bottom. And it turns out that these numbers are different. So when you get a report of the amount of freezing rain that's fallen, you have to know whether it's the one on the top, radial ice, or the bottom, flat ice. And so right now we're using what's called the freezing rain accumulation model. That's something that's used operationally to estimate ILR in the Weather Service. And in talking to the creators, they've said that they kind of expected it to be replaced by now because it was a relatively simplistic way of estimating ILR. And we think that AI might actually make that possible to do in real time with a product like Frana. And not only do we hope that ILR can be done by AI, something we hope to get started pretty soon, we're also examining the possibility of using AI to process reports. So for instance, if somebody calls the Weather Service and says there's a bunch of freezing rain on the power lines, there's a quarter inch of ice, well, that's a radial ice thickness, but it doesn't use the word radial. So we hope that we can train an AI to classify radial versus flat as we get ice reports in. Second piece of this is similar but different, is snow rate, how much snow is falling. The problem here is a little bit different than ice. The vast majority of snow measurements are once daily manual measurements. It's somebody going in their backyard, sticking a ruler in the ground and reporting how much snow is there. And that's a problem if you're wanting to do things on anything shorter than a daily time scale. On top of that, much of our research on rates with snow focuses on the liquid equivalent or melted depth. If you take the snow that fell, melt it down, how much liquid is there? That has more work that's been done on getting that answer than how much snow depth is there. And even though that's been relatively well researched, it still has large error bars when you compare it to the amount of liquid and rain. But if we have that information, we're still going to need the snow to liquid ratio, SLR, very similar to ice to liquid ratio, to go between the liquid equivalent and snow. We're developing experimental snow rate field for MRMS that again uses spectral bin classifier to determine where snow is falling. Again, uses the hourly MRMS QPE for liquid equivalent precipitation. And then snow rate is relatively simply a QPE times a snow to liquid ratio for every snow grid point. And like ILR, with SLR, there's been relatively little work on what a good SLR is. Many of the ones used in operations are very simple and had very little vetting. And so prior to the project that we're working on now with CPO, got together with my collaborator, Peter Veals, and they've been working in Utah on a robust AI-driven SLR algorithm. I'm going to hand it over to Peter to discuss their SLR algorithm. Peter?
Thanks, Andrew. Yeah, so as Andrew mentioned, the SLR algorithm that we developed, we began with acquiring a training and testing data set that consisted of high quality manual observations. So the picture here of a manual observation being taken, the way that it's done is you have a board that's placed atop the snow. The observer then measures the depth, and then in a coring tube measures the liquid equivalent of the snow, or SWE, snow water equivalent, to get the SLR value. And the reason that's important and a difference compared to what's been done traditionally is that the data sets that have been done to date are made from gauge data. So the liquid precipitation equivalent or snow water equivalent is obtained from these gauges. And the reason that's a problem in snow is air, when it's flowing over the gauge, lofts some of the snow particles and they don't fall into the gauge. It's a process known as undercatch. And if you look at a figure here that depicts undercatch, Andrew, if you can just advance it a little bit. For just a 6 meter per second wind, even with a shielded gauge, you will only be catching potentially 70% of the precipitation that falls. And so that's also difficult to tell when and how much you're under catching. So this is a huge source of error in snow to liquid ratio algorithms that have been trained to date. Next slide. So we did 2 phases of this research. The first focused on the Western US, and this paper's been submitted to Weather and Forecasting. It's in review. In this, we obtained data from 14 sites across the West. The reason we focused on the West here is twofold. One, there are these really high quality sites that are maintained by snow safety professionals. So these are places where avalanches threaten lives and property. You have professionals collecting these snow observations once or twice a day. It also snows a lot in these places, so that you get a huge data set for a relatively short period of time. One of these sites, Alta Collins here in Utah, got 907 inches of snow in the 22-23 winter season. And the other reason is that this is a huge data hole, and this is a place where traditional snow to liquid ratio methods have woefully underperformed for the applications that are needed across the Western US. That's why this was the focus of the work. The next phase, Andrew, if you can advance, the next phase of the work was expanding to the full CONUS. So this was, of course, an issue because we didn't have these professional observers taking these obs. And so what we did was work with the COCORAS folks to send out an email to all the observers to self-identify those that were taking these manual obs using this very nitpicky process to get the proper way of measuring SWE, snow water equivalent. So that yielded just under 14,000 obs from 921 sites. Next slide. And so we used these obs to train a random forest algorithm. We did it for the West and for the full CONUS. I'm just showing the full CONUS results here, or full CONUS process here. So we selected training variables based on prior studies and also what yielded the best performance of the algorithm at our sites. These were obtained from the ERA 5 reanalysis for the period 2000 to 2022. And then we applied them, and what you'll see in the next slide is that we applied them to just the HER data for the period 2022 to 2024. And so that's what I'm showing here. So this is a completely independent data set of what they were trained on. So the results focus on the boxes there in each figure. You can score the performance based on R squared and mean absolute error. That's what we did. And you can see the random forest is what we trained here on the left. The other three to its right are the current algorithms that are used in the National Blend of Models. So you can see this AI-driven algorithm was a huge increase in skill relative to what was used or what is currently used. And we're working with the folks at the Environmental Modeling Center to get these into operations. So one issue, though, that affects all of these algorithms, including ours, is this situation where they have a hard time predicting the high SLR events. So the events where SLR is high, they tend to underperform. So next slide, if you could, Andrew. And it turns out this is not AI's fault. So what I'm showing here is a graph for the Western US. Andrew, you can toggle back and forth a couple times and you can kind of see the improvement there. So this is for the Western US. This was our algorithm. And for the West, it turns out one of the variables that was skillful that we trained to was actually QPF from the HER. That was not the case for the full CONUS, but for the West, it was. And what Andrew's toggling between is if you use observed SWE instead of QPF. So this is if your QPF was a perfect forecast of the liquid that fell. And the reason there's such a huge improvement there is that it turns out QPF, or sorry, that the liquid equivalent is actually a really important variable in predicting the SLR. And the physical basis behind that is that the more snow water equivalent you have in a storm, it compacts the snow under its own weight, so it densifies itself. So that's one of the physical limitations, of course, of this AI is that you can't predict perfectly without the physics behind it as well. And I'll let Andrew wrap up here for us.
Okay, thanks, Peter. So to kind of bring this back together, I wanted to say quickly where we're going. Where do we think we can go with this when we have the answers to these questions? I'm going to use an event from 17 February 2022. This was a heavy onset snow that caused dangerous travel conditions in northern Illinois. There was a 100-car pileup on I-39 that closed the interstate till the next day at 2015 UTC. And so in the left here, here's a figure showing snow intensity. On the right, a figure showing prob-SR. And so at 18 UTC, if I highlight I-39, for the northern half of the interstate, you had relatively light snow, but low, high prob-SR. So you had light snow probably accumulating on the roadway. Southern half of the interstate, you had heavier snow and lower prob-SR values. So while it's snowing more, that may be melting when it hits the pavement. So while there's reason to be concerned, it's not critical at this time. But if we advance to 20 UTC around the time of the pileup, now you have high snow rates everywhere, high prob-SR everywhere. Our partners, this would be much more concerning to them. And it turns out that this was about the time of that big pileup. So meteorological parameters, getting the information that our decisions partners need to make decisions is absolutely important. And that's where we're trying to go. So to close up, we're using AI to impacts. What's falling? How quickly is it falling? And is it remaining frozen or freezing on the ground? AI is providing opportunities to address challenges related to winter weather, but limited or uncertain observations require careful consideration when you're applying AI to a problem. One of the things we do wonder, though, is if we say we have struggling to develop an AI in a certain area, can this drive us to fill in these missing observations or improve observations? It's also important for effective use of AI to understand both the available inputs, what goes into your model, and the available verification. You know, what's garbage in, garbage out is true here, and you have to know what you're feeding your model and what you're verifying against to know the question you're answering. So I'd like to thank you all for your time, and if we would love to answer any questions. And our emails are also here on the slide if you think of something later.
Great. Thank you so much, Andrew and Peter. We do have time for a question or two. So we had one come in. Um, we're asking, is it possible to use satellite digital elevation and changes due to snow accumulation to generate training data for your training and prediction?
Yeah, I can take that. So a lot of I think probably the person asking the question is referring to these like LiDAR based or satellite based snow analyses where you get the change in depth of the snowpack. And yeah, you can certainly get a number of important variables from those, but that interestingly still requires a snow to liquid ratio because those satellites are just measuring the depth of the snow. So if you want the water variables, which are important in a lot of places, particularly the West, you still need to apply a snow to liquid ratio to the freshly fallen snow to figure out to change that from depth of snow to liquid of snow. And that's a situation where actually that you can train using observed SWE instead of forecasted SWE. And so you could get even more skillful for those analysis type applications.
Great. Thank you. Just one other question. Would it be better to use more complex methods such as CNN?
Yeah, so I tried at least, Andrew can comment on their application, the random forest. For mine, for SLR, so we tried a neural net, we tried a multilinear perceptron, and um, and support vector regression too, which is not, I don't believe that's a neural net, that's another type of machine learning. The support vector regression was the only thing that was more skillful than the random forest, but it was an order of magnitude slower. So we didn't find that useful for operations. And then the multilinear perceptron, the MLP, was actually less skillful than the random forest. So the neural net was not as skillful as the random forest.
Yeah, I'm just going to emphasize the similar things to Peter that we do a lot of research operations here. And so the random forest in our testing for the ProbSR was just the right balance of performance and speed because we only have a certain amount of computation time available for our products as we generate them. So, the something like a CNN that's computationally more expensive has to both prove its ability to do better and fit in the space we have. And often the cases, it's the space that we have on the computer that's the problem.
Great. Thank you again so much, Andrew and Peter. For the sake of time, we're going to move on to our next presenter. But if you are a participant and you have more questions for Andrew and Peter, I encourage you to please keep sending them in and I'll pass them along. We're going to move on now to our next presenter, Tian Yang. He is an associate professor at the University of Oklahoma in the School of Civil Engineering and Environmental Science. He'll be presenting his work today on how AI and machine learning could improve subseasonal to seasonal precipitation forecasts, including work that contributes to a project supported by the NOAA Climate Program Office's Climate Variability and Predictability Program and the Modeling, Analysis, Predictions, and Projections Program, focused on improving our understanding and modeling of key processes of coupled drivers and contributions to total water levels. So thank you so much for being here, Tian, and go ahead.
Sure. Thank you, Clara. I'm sharing my screen. Just to begin with, and by training, we are hydrologists, and we also do quite a lot of machine learning AI work from a very long time ago, and within different fields, within water resources engineering, also hydrological sciences, and as well as the weather and climate sciences, particularly in the field of precipitation forecast in the scale of subseasonal to seasonal scale. And just a short background, before I started my faculty career, I did spend some time in Deltares, USA, as a hydrologist working with the NOAA's National Weather Services CHIPS program. And so a lot of our research is towards operational applications. So over this talk, you will see a lot of our research and thinking is towards to improve the hydrologic applications, especially using some of the new subseasonal to seasonal precipitation forecast. Our research motivation really started with this paper from 2017, almost 10 years ago and 8 years ago, in which it showed that a lot of those forecast skills will decrease as the forecast lead time increases. And all the way over the 1 to 10 days range, you will have a very sharp decrease of your forecast skills from very excellent to basically zero. Also, over the seasonal and longer time scale, you'll have a slightly improved forecast skill. However, during the middle, it called this forecast skill desert, which the forecast skill score always start from poor and quickly decrease to zero. This is where the weather scale phenomena and the large scale climate interaction, they confound each other. As a result, a lot of those forecasts has to consider both weather scale events as well as how the climate will impact the regional weather patterns. And of course, the forecast skill here include all the variables. Precipitation probably is the most challenging one among others as compared to temperature. So over this talk, I will quickly give some sampler of the research we do, and also contributed by one of my prior student, Lujun Zhang, now is a postdoc in my group. We have done a sequence of research regarding the subseasonal to seasonal precipitation, adaptation, and verification, and hydrologic applications. Start with the work over the few hours to 2 weeks. We have a numerical weather prediction model which can provide a relatively good and reasonable precipitation forecast. And also over the longer time frame, over years or decades, climate model or Earth system models are widely used to do. The question is really over the 2 weeks to a month period, what do we have and what's the reliability of the forecast over this particular subseasonal to seasonal period. Having reliable forecasts, especially precipitation, is very valuable for reservoir operation, agriculture practices, irrigation, food production, and also all kinds of water transferring and allocation planning and management. Also, over the existing program and efforts, we do have a couple project internationally contributed project from different countries. And over the Europe, we have the ECMWF, the European Forecast Product, can provide a medium-range forecast. Over the US, we have NMME, North American Model Ensemble, Phase 1, Phase 2, and also the newest Sub-C or Sub-X product. Also in Canada, we have Environment Canada. So among all those products, the internal strategy are very similar. It basically uses the coped climate model or downscaled GCM or Earth system model to fill the S2S gap over this particular period. And also it tries to include all kinds of different models, try to reduce the single model errors. So our first piece of work is really to evaluate how accurate those S2S forecasts, for example, from the US project, the NME2, what are the levels of accuracy, reliability, and confidence in the forecast. And so Lujun started his PhD with me by evaluating the North American products. There are 4 different models that are contributing to the NME2 project. And the conclusion here from this paper, of course, you can download and see the full text. Our conclusion is that the accuracy and the skill score of the raw forecast from the US products really heavily varies by different model, by seasonality, and by the forecast lead time, and also by regions. And there's a significant amount of uncertainty and errors in the raw S2S forecast, especially for precipitation. To give you an idea, this is a one model, and the color bar shows the percentage of biases. Compare the forecast to the observation over the corners, and among different seasons, this is a one single model. You can see the forecast bias can all the way from range from the 100% overestimation to 100% underestimation by different seasons, from winter to spring all the way to summer. And also, among different models, we see very similar things, and the arrows quite swept from overestimation to underestimation. And even within one season, different model can give a different results. And some model may overestimating the precipitation, some model may underestimating those precipitation. So there are a lot of uncertainties and biases in the raw weather S2S forecast. Also, we evaluate the anomaly correlation, ACC, by different model. We see very similar things. From week one, the ACC value can start with the 0.3, 0.4, and quickly it will reduce to 0.1, 0.1 after 2-3 weeks. So the forecast skill also decrease quickly after 2 weeks. So not only the US base at the specific river basins, the S2S precipitation forecasts are also problematic, at least for hydrological applications. So here is just one piece of case study currently we are working on with the on the Upper Colorado River Basin. And what you'll see here is the Upper Colorado River Basin, and we just pull the NMME2 precipitation forecast, Jeff's version 12 forecast, and also compared to the observation. What you see here is the one-day forecast of a precipitation over about 20 years average, and the NMME doesn't really capture a lot of those high precipitations at the upper locations of the river basin. And this is may also be something that the snow will contribute, as Andrew talked about earlier. And also the GFS captures some of the high precipitation events, but not all. And some of the low precipitation area, there are still a lot of uncertainties. As we go with the 14-day forecast, there's not much change. And also when we go to 28 days forecast, the results are just very similar. And with this coarse resolution, it's really challenging to put those data into hydrologic applications. So the second question we ask ourselves is, are those S2S forecasts useful for medium-range hydrological forecasting? So to do that, we developed another study published in JHM. And the goal here is to verify whether those forecasts from the S2S product can serve as an alternative approach for the medium-range springfall prediction. Just a slight background in operation. When we talk medium-range springfall prediction, we use a hydrological model. We can first split up the model and calibrate the model to the current time. And here is what we calibrate the model. And for the future forecast in operation, there's a ESP framework called a Ensemble Springfall Prediction Framework. Basically, the idea here is to randomly draw, resample the precipitation from the past, and make that or use that as a proxy for our future forecast, especially the precipitation forecast, and put that into the model, hydrologic model, to simulate the future scenarios of flows. So this is the what we have right now as the benchmark, and our idea here is instead of using the randomly sampled precipitation with the dynamic precipitation forecast from the NMME project, we can directly use the forecast to drive the calibrated hydrologic model to estimate how well they can capture the flow regime. So to do that, we select a couple watersheds in the southern part of the country where we are located in Oklahoma. And the color line here shows the KGE value of our flow simulation, and the different color shows the forecast, the hydrological simulation driven by different models forecast precipitation. And as compared to the benchmark, you will see a lot of those, most of the model, they derive a higher KGE value, meaning the S2S forecast, they show some skillful capability in driving these hydrologic model to obtain the stream flow prediction. And also, at a single events, we can also verify the S2S forecast capability in hydrologic application. In the top row, you see this is the conventional ESP approach, and the red line here is to observe the high flow. It's a flooding events happening in 2022 November. And by randomly draw the precipitation, basically there's no way you can capture this high flow. However, by using the S2S forecast, there's always a possibility that you can capture some of the flow, especially for the high flooding events. So also the S2S provided some type of uncertainty bounds so that we can estimate how well the probability forecasting for all kinds of flooding events. Just to quickly conclude those two pieces of work, we find out that raw NMME precipitation forecasts, they contain high uncertainty and significant errors in the raw forecast. And however, the use of S2S precipitation forecast as the input to hydrologic model will still be very useful. And we demonstrate in most of the cases is much better than the conventional ensemble stream flow prediction approach for medium range stream flow prediction. Though they improve the flow forecast skill, they are slightly limited. Going forward, we are wondering whether AI and machine learning model can really help in correcting the raw S2S forecast, and so that we can obtain more reliable and better forecasts for the future, especially for the extreme precipitation. Therefore, we developed another study published in Atmospheric Research a couple of years ago. And in this study, we basically used the same random forest regressor as Andrew used in their work to post-process the raw S2S forecast. And here, the input to the AI machine learning model, they include the forecast variables from the same MME2 project, including temperature, geopotential height, and also the past forecast of precipitation. And then in this work, we work on the 99% higher quantile of the precipitation, basically the high events, the extreme events over the corners. And this is our result. The first row you see is the Brier skill score, BSS, over the corners for the extreme value. And BSS equals to 1 means there's a perfect forecast. BSS equals to 0 means there's no improvement at all as compared to the climatology. And if we see a BSS smaller than 0, meaning the forecast quality is even poorer than the climatology. So the raw forecast will give you the extreme precipitation forecast skill score over the corners about 0.06. This is the average number of all the BSS numbers over the every pixel. And with our AI machine learning improved the forecast, and we can see that over week 1, we got a quite significant improvement for capturing the extreme value of the precipitation forecast. And even with the week 4, even though the forecast still decreased rapidly, we are still gained a lot of more confidence than the raw forecast to capture the high values in the precipitation events. Also, we further evaluated the PDO, probability of detection, and also false alarm. And in here, what you see is the kind of receiver's operating characteristic curve, AUROC. This value, the higher the better. The ideal value is 1. And what we found out is still in the central part of the US, the forecast skill is very challenged. And you will have a very low forecast skills. And even with the machine learning model, we see some improvement. However, the improvement is still worse than the West Coast and the East Coast for most of the part. So the conclusion of our third study here is that with some supervision in designing the machine learning AI model and also the hyperparameter as well as the different hydrometeorological inputs, even a basic AI model from random forest can reasonably improve the raw S2S precipitation forecast over the CONUS, especially in predicting the occurrence of the extreme events. And here we also did some study using the more complicated machine learning tools, and currently we are developing some more so-called physical informed or physical aware spatial machine learning approach. And we hope that will give us more confidence and accuracy in cracking the rainfall. Moving to the last research question, since we have demonstrated that some improvement in the S2S precipitation forecast, how well will the improved forecast will give us more confidence in hydrological forecasting? That's our last piece of work, also published in Journal of Hydrology. So in this work, basically we compared the two scenarios. This is one of the commonly used approach. Once you have a raw forecast with the coarse resolution, you can always do a bilinear interpolation to make it finer, and then do a contour mapping to remove the biases. This is the typical post-processing approach that's applied in all kinds of weather forecast or climate forecast. What we do here, we instead of directly putting in the QM, the contour mapping, we embedded another AI machine learning bias correction method. We hope the AI tool can capture some of the spatial and the temporal correlation and give us more confidence in the hydrologic application. And so basically, there are two scenarios we have compared in this work. One is the conventional way of only using the ECSD approach for post-processing the precipitation and run into a hydrologic model. And the other way is our proposed one. We run an AI embedded approach into the entire post-processing procedure. Hopefully, that will derive a higher skill score in the flow simulation. So as the one piece of result, what you see here is the flow simulation result, and characterized by the continuous ranked probability score, CRPS, and for different watersheds. And this CRPS skill score 0 is the ideal value. So the lower the CRPS, the better. The red line here shows our proposed approach with the AI embedded post-processing procedure, and the black one is the conventional ESP approach. So as you can see, most of the lines from the red is much lower than the black line, meaning at least we improve the forecast skill for the flows quite a bit, and especially over the first few days all the way to maybe 15 days, and we see most of the red line is below the black line. However, once we go to the longer forecast period, the black line started to show lower skill score, meaning that's a better forecast from the hydrology perspective. So after the 14 days, the traditional ESP approach still has a lot of skill scores and probabilistically better than the S2S precipitation-driven scenario for the flow simulation. And also we evaluate the precipitation results, and we observe very similar things. And our approach, in this case, shows a more higher skill score than most of the traditional approach BCSD, and also the raw forecast. So this is the precipitation result, and we want the red line as higher as possible. And so here we demonstrate that some of our AI corrected approach is much better than the traditional way. And so basically, that's a very slight sampler of the research we do here in terms of the weather and climate forecast, and especially on the precipitation side. And over those 4 different studies, over the first one, we demonstrate that we comprehensively evaluate the NMME2 precipitation forecast and evaluate the bias, forecast skills, and also the dependency of a model region, lead time, and seasons, and already identified there's a significant amount of errors and issues, especially with the raw precipitation forecast from the NMME model. Then we also demonstrate that even though there are errors, the use of S2S ensemble precipitation forecast are very useful and for assisting the spring flow simulation, especially when we talk about the medium range spring flow prediction. S2S forecasts are still very valuable, and we think will be the future to drive a lot of those operational hydrologic forecasting. But some issues still remains. Then we also explore how AI and machine learning tool could help in correcting some of the raw S2S precipitation forecast, and also investigate how the AI machine learning models capability in providing more skillful extreme precipitation forecast over the NMME projects. And last but not least, we also explored how the AI machine learning tool could be used as the embedded approach for post-processing the raw forecast, and also put that into the stream flow forecasting into the hydrological context, and demonstrate that in our selected watersheds, there has been more skillful forecasting from the flow and the river forecasting perspective. So that's pretty much our conclusion, and here are some take-home message. We also feel those are the challenges for S2S precipitation forecast. Especially, we think there are a very coarse resolution. Most of the model is 0.5 degree, meaning 50 kilometer square box, and that's very challenging. For hydrologic application, we have to do a lot of post-processing. Also, the ensemble size ideally could be larger, and because from the conditional ESP approach, we can easily generate 40 or more ensemble members. However, in the current NMME or sub-X archive, there are only 10 or even fewer ensemble members in each of the model. So the higher ensemble size, the better for us to evaluate the hydrologic implications. Last but not least, there are some challenges, especially from the application side for our research with regard to the low hindcast frequency. NMME only covers 30 years period over the past with the monthly frequency. As a result, there are only 400 samples, and that's also there's a slight challenge to run some of the more complicated machine learning models, such as convolutional neural network and or the LSTM models, and we have to really consider how the sample size will influence the accuracy of training some of the data-driven models. And we landed the random forest, the tree-based approach, similar as Andrew and Peter, but we hope with the increased amount of the data and the handcast frequency, we shall be able to run some more complicated models. So this is my last slide, and we'll be looking for potential collaborations, project, conference sessions, workshop, and also all kinds of K-12 undergrad or graduate student training and education activities. Here are our email, myself, and also my postdoc, Dr. Zhang. And feel free to reach out to us if any questions. Okay, Clara?
Thank you very much for that great presentation. I think we have time for one quick question. We had one come in. We have someone wondering, why is the skill of the central region worse than the east and west coasts, both in the S2S model and in the random forest prediction?
Sure. So this is related to the mesoscale events, and for example, over the west coast, the Pacific Ocean will bring a quite large amount of water vapor to the west coast, and over the center of the country, there are a lot of uncertain, unpredictable subseasonal events, and such as the convective storms and convective events. It's really a very challenging area for the central of the country. And actually knows this in Oklahoma, the weather is very random. And it's really the mesoscale events that are driving the challenges over the middle of the country. And over East Coast, from the model, it shows slightly better results. And similarly, when you run a machine learning model on the raw data, if the raw data has a more skillful prediction and skills, eventually the post-processed result will be slightly better. Over the central part of the country, we think there's a lot of rooms we can do research and try to improve the results.
Great, thank you. That's the only question we have time for, but thank you again so much, Tian Tian, for your presentation. And I'm going to share my final slide here and thank all of our presenters for joining us today. And thank you to all the participants who tuned in. The Climate Program Office, CPO, and the NOAA Center for AI, NCAI, is really excited to host some more webinars in this series. Next Friday, we'll be hearing from researchers using AI methods on their work in wildfire research. And on April 29th, the speakers will focus on AI as a tool in studying climate variability and extremes. So I put some resources in the chat for learning more about NOAA Climate Program Office and the NOAA Center for AI. You can also feel free to reach out to me directly with any questions about CPO, NCAI, or this webinar series in general. So thank you again for joining us. Thank you to Andrew, Peter, and Tian Tian for sharing your important work, and we really enjoyed learning about it. And we'll see you soon. Thank you.
Thank you. Okay.